Hello, I'm John Shavacco, the co-chair of the NIGEO 2023 conference and a board member of the New York Geothermal Energy Organization. I'd like to welcome you to this recording of a live presentation from the conference, a two-day event which was held in Albany, New York on April 26th and 27th of 2023. This year's educational sessions and keynotes represent the latest in ground source heat pump system design, product innovations, and installation practices, along with important policy, regulatory, financing, and incentive updates. This presentation is one of over 40 sessions from the two-day event, all of which were recorded and available at NIGEO's website, www.ny-geo.org, along with session descriptions and a link to download the slides from each of the sessions presented. NIGEO is proud to make this content available to our members and other industry stakeholders, and if you are a member, thanks so much for your support and participation. If you find this content valuable and for some odd reason you are not yet a member, consider joining NIGEO at the appropriate membership level with details available at our website. The live recording from the NIGEO 2023 conference will start in just a moment. Thanks so much for listening.
So yeah, I just wanted to start this talk with a little bit on safety around compressed air. Tell you a little story from 1996. I'm kind of dating myself, but I do that every Saturday night anyways. So yeah, so I was working on a ski lift way up the mountain. We had to hike in every day, probably a couple miles up the mountain, and we were jackhammering and drilling for blasting in the rock. And they ran a 100 psi line, 4-inch 100 psi PVC line from a compressor station all the way up the mountain, and had T's on it for the lift sites or for the tower sites, so we could jackhammer and drill there. I ran up to open the valve. Someone was holding a jackhammer precariously and needed it opened real quick, so I opened it quick and the hose blew off. The whole line went sideways and hit a rock, and I was looking down the line and I saw a rapid sudden fracture down the entire line, and it filled my ears flush with dirt. So I jumped off the mountain. I jumped really far down, and when I landed, people were calling me. I couldn't hear them because my ears were full of dirt. So I got nerve damage from that. My ears have been ringing ever since then, but I was okay. Luckily, I didn't get any shards of PVC, but when you look down a line that's a couple miles long and you see sudden rapid fracture on PVC with high pressure air in it, you know to look out, all right? So on a lot of drill sites and stuff, I see a lot of compressed air, high pressure water around, hoses in different conditions, so look out for yourself. It happens. It's not the only time I've had stuff blow up in my face from other people messing up, so a little safety there. Anyways, I'll get started. Systems should work the first day they're handed over to the owner. The purpose of the sequence of operations is to define how the components of a system will interact through its various operating modes. So our presentation outline, we'll go through the learning objectives, description of some of the energy sources and sinks that can be used, not all of them. We'll go through things to consider when integrating energy sources and sinks. We'll look at energy plant considerations. We'll look at an introduction to the single pipe layout for large geothermal systems, which is a big topic right now. I'll do a depiction of the single pipe system demonstration project that we've been doing over the last couple years and optimizing the sequence of operations for. So don't leave because it's too simple at the beginning, because it gets into depth. But I'm starting simple so we can build it up so for the benefit of everybody. And then we'll get into the sequence of operations for the demonstration project and then go into a question and answer period. So I'm going to try to rip through this. We can go back at the question period if it's too fast. So after viewing this presentation, it's our intent that students will be able to, 1, identify common energy sources and sinks for networked geothermal systems. 2, consider key elements of integrating energy sources and sinks. 3, understand the concept of single pipe district geothermal systems. 4, recall the challenges with the single piped system demonstration project. 5, understand and use the sequence of operations that was developed for the demonstration project. That's the goodies, I'm giving it to you for free. Some of the possible energy sources and sinks. So they can come in many forms. Energy sources, earth materials, groundwater and surface water, like traditional geo. We've got waste energy from refrigeration processes, it's a big plus, and industrial processes. Solar thermal, we've used that for reheating frozen ground loops and saving them. Drinking water systems, wastewater, clean wastewater is what I'm more of a proponent of than dirty wastewater, like out of a wastewater treatment plant, let's say. Power plants, thermal power plants put off a huge amount of thermal energy all the time on their condensers. Data centers, hot topic. And then industrial processing plants, we have tons of waste heat. Energy sinks, so places to put the waste energy. Traditional geo, snow melt or freeze protect systems work quite well for cooling off geo. Domestic and service hot water systems can always be used. Drinking water systems, wastewater, and industrial processing plants. All good? Okay. Things to consider with energy integration systems. So there are many things to consider with energy integration networks. A few of the key elements to consider include ideal temperatures for sources and sinks. So, like for instance, I've seen people trying to use an ice arena compressor directly for heating a building. So they decrease the efficiency of the ice compressor permanently for its whole operation by setting the head pressure higher. They stress out the compressors and they wear parts more and just consume a lot more energy. And the compressor's running more for refrigeration than it is for building heating, so they're really compromising the efficiency of the biggest motors in the plant that run the most, so it's pretty silly. Then you'd want to put a heat pump, like have an intermediate loop between the two and then put a heat pump on it. So the ideal temperatures for sources and sinks are sort of ambient middle temperatures. You don't want to try to boost things too high or take them from too low. If you have to, maybe you want to put a cascade, a couple heat pumps in there just so that the whole system can run at a more efficient temperature rather than, say, bringing the source temperature down on the whole system and compromising everything. That's a big thing. Timing of different loads, so you might need storage and or controls and ways to deal with the timing. You might have your heating loads happening at a far different time than your cooling loads, or they might coincide quite closely, and then you can really reduce your ground loop size in your storage. Pumping energy use and optimization of pipe sizes. So really, we can crank up the pumps in the sequence of operations during peak times and have smaller pipes, and then run the pumps on lower speed during the rest of the time. Just depends on where you are with your velocities but you can really save a lot of piping cost and energy by having an intelligent control system. Maintainability. So this means like being able to turn off the system and fix leaks, things like that. Seen some pretty horrible things where we weren't able to turn off the heat pumps in the buildings and the whole system leaks. Major leak, major failure. All the antifreeze gets pushed out of the leak. They can't afford to put new antifreeze in, and so they shut down the system for the winter, and nobody's got backup heat in their houses for 60 houses. That was really fun to deal with. Now, they didn't want to tell anybody, so we get to the next point. User engagement, very important, particularly when things go wrong, and they always do. So really having the user engagement, a forum set up, being able to answer questions, having a good person on your team who can answer the technical questions is way better than trying to hide your problems, because when you try to hide your problems, the community bands against you because they can see through all that. I've seen it. Proper third-party commissioning, provider engagement would be, having someone who's third party to the engineers and the contractors, so when there's infighting going between them, you've got someone who's on the owner's side trying to help figure out what the truth actually is. It's usually a mixture of the two. Ongoing monitoring and early intervention, nothing works first try ever. There's been no control system I've ever programmed that I got the first try. And I'm pretty good at it, but it always needs to be tweaked in some way. It's never perfect the first time. So you really need to monitor it, reprogram it, retest it. Conflict of interest, documentation of promises and results for warranty claims. So that's where we get the third-party commissioning provider to document all the promises and what's been done in the inspections, and that's been signed off on. So if it's not working, maybe the people who did the design and or build might be in a conflict of interest determining what's wrong. Energy plant considerations. So we've got a heating or cooling plant with seasonal changeover. So the heating example here, you've got electrical energy going in one unit. So each arrow is a unit of energy to depict it graphically. Then we have 3 units of energy going in and 4 units of energy going out. So our coefficient of performance in heating is 4 because we have four units coming out and 1 going into the electricity. What you got divided by what you bought. And we've got the opposite happening in cooling. We're taking 4 units of thermal energy out, putting 1 unit of electric energy in. Our COP is 4 again. Pretty simple. So now we have the typical hot tank, cold tank system with 3-way valves to change it over. This is a refrigerant changeover system. So the ground loop side's always the ground loop side and the building side's always the building side. The building side's on the right in this picture. The COP is often equal to or less than the seasonal changeover due to valve leakage and cross connections. And I put an exclamation mark there because most people don't know this, but a lot of 3-way valves actually have leakage, and they have it in there so that they can relieve pressure from the coil of an air handling unit or whatever, and it's not, when it's actually switched off from the expansion tank so that you don't burst pipe. So when you're selecting these valves, it's really, really important, because if you're having leakage from the hot tank to the cold tank, the system will just go into heating mode and then into cooling mode and then into heating mode, and you're just fighting leakages across the system. That's not very efficient. So that's why I say it's often equal to or less than the seasonal changeover. You have to prioritize heating or cooling because they can't be provided at the same time, and expensive valves are required for this system. Cooling mode example, same deal. It's just switched over to the cold tank. Now we have a water changeover system with 3-way valves. You could do this with a bunch of 2-way valves or 6-way valves as well. The COP is often greater than in the previous modes. You can provide simultaneous heating and cooling. So this is a heating mode example on this slide. 2 additional expensive valves are required. It pays off. Consider equalizing the hot side and the cold side circuit pressures between mode changes. So what can happen, even if you have an expansion tank on both sides of the system, is that when it turns over from one to the other, you can actually lose fluid out of your pressure relief on the one side. It's a little bit of a conversation on how that happens, but my advice is to turn off the heat pump between modes and then have both sides of the system connected while no pumps are running. So then you can equalize both tanks and you won't start losing fluid, because then people think you've got a leak in your ground loop, and it's a real kind of fight to convince people you don't have a leak in your ground loop, and then find out that, oh, it's just switching over, and yeah, it's dumping some fluid out that pressure relief. That's from experience there in the field. This can also be done with 6-way valves or banks of 2-way valves. So 2 6-way valves or 8 2-way valves per heat pump or per cluster of heat pumps. And then consider the timing of loads and the time to switch modes. So I put the load banking concept here because I did a system like this and I was monitoring it, and it was spending a lot of its time in switchover and delays and the valves, and so I wasn't getting enough heating for the pool from my heat pump when I was trying to pull the energy from the building. But the energy from the building, the load wasn't huge, but the pool is pretty huge. So we're cooling the building, and then we're switching over into ground loop, pulling energy from the ground loop and putting it in the pool, and then we're switching back to doubling efficiency by pulling it out of the building. And that switch over time made the backup heat come on to heat the pool. So what I did is I said, okay, well, if we're running along in heating mode, already, and cooling is required. Heating mode has to run for a certain amount of time for cooling mode to come on. So it kind of does a thermal banking of the cooling system. The cooling system ran up in temperature a bit, but we're still meeting load because it was cycling on and off anyways. I did the same thing in cooling. So if cooling mode's chugging along and we need a little bit of heating, well, we'll let that tank drop a little bit and then go over to it later. And then actually when it switches over, it has longer time in simultaneous heating and cooling. This is critical. This is really important. Ask me about it. It's a big concept. I wrote a whole article on my LinkedIn on it. So yeah, it's really something I learned the hard way, and it took me a sweaty couple of weeks to work it out in July till I got it fixed. So here we've got it in cooling mode. We're taking energy from the cold tank and putting it into the ground loop. And then here we've got the double efficiency mode here with the heating and cooling happening at the same time to two tanks. So energy plant for 4-pipe district energy system assisted by distributed heat pumps. So we've got, let's say this is a plant that's connected to a system that has chilled water and hot water being pushed around the system. So you're a user, you're going to be paying for any heat you take off the hot water loop or any cooling that you do, energy you put into the cooling loop. So you're going to pay either way where you connect to that, but you're a user. There's a really large project that I looked at, and their design is pretty far along way. We couldn't really change it. So they have like a chilled water loop that's served by one heat pump, and then a heating water loop that's served by the other heat pump. So all the residents are going to be paying double the cost for the compressors to run when they could just be taking energy out of the chilled water loop and putting it into the hot water loop, because it's a mixed residential, commercial, big development that's going to have simultaneous heating and cooling every day of the year. Even if it's all full cooling mode, they'll still have a huge domestic hot water load. So I kind of came up with this idea on like how later on, how can we help the users save money? Well, if we ensure that there's a bidirectional energy meter for this to work, what we can actually do is take the chilled water return from the building and put the energy into the heating hot water return when the building has a simultaneous heating and cooling load. There's a note here. This is just an idea. I've not had a chance to put this into practice yet. But anyways, it's just an idea. So in a heating mode example, now if you're actually got a bidirectional meter, so you're helping the chilled water loop, then you go and take your energy out of the district energy chilled water loop and put it into the heating hot water return in your building. So now you're actually, instead of paying for heat off the district energy hot water loop, you're actually helping out their cooling plant and then getting a refund for it. So here's a load assist example. Oh, sorry, this was a cooling mode example where you're putting it into the heating hot water loop to the district energy from your building. And then this is the load assist. You get the idea anyways. So you can do it either off the hot water or the cold water loop, and then, yeah, or do simultaneous heating and cooling on your own building side. So even if they've done an inefficient system like the one I was talking about, you can still do something in your own building, because you're not going to change a central plant in that kind of system. It's be pretty expensive. So this is our single pipe district geothermal pilot. So we can see okay, there we go. Energy transfer station right here. So this is We call this an energy transfer station, and this one as well. These are ground heat exchangers with their own pumps. And we got the central pumps here. And we've got a typical primary, secondary connection with separate pumps in each station. So we had a heating dominant load, a swimming pool here. We had a bunch of cooling heat pumps, forced air units here, and a bunch of cooling ones here. So that's the introduction to how it started. I was asked to do the controls for it. Some advantages are the lower cost of piping, hydraulically disconnected to the loads because you have your own pumps going on primary, secondary, so your hydraulics work quite nicely. Low energy pumping, if you do it right. Energy sharing, obviously. Large surface area available for multiple ground heat exchanger zones. So that means when you're not at peak, you can still run your pumps to the ground heat exchangers all together and get a huge surface area. And yeah, you're not going to be turbulent in those ground heat exchangers, but your water has a ton of residence time to sit there and just collect energy, so, or reject energy, transfer energy. Some disadvantages are the maintenance on the main line shuts down the entire system. That's a pretty big, like all your eggs in one basket consideration. So you need to be able to signal to all of the buildings on the system and say, hey, we've got a shutdown here. We need your plant to shut down and go to its backup. And that should be happening automatically. You don't want to go and knock on doors because you don't want to have to be running the system when it's leaking. You want to close it all off. And having valves in all the right places is good. Backup heating and cooling is required. More complex controls. Special sensor requirements. So you want long temperature sensors to go into the main line. Otherwise, you're not going to really be measuring the temperature of the water in the middle of the pipe when you're in laminar flow, because that probe, if it's on the outside of the pipe, is only going to be measuring stagnant water. And then you have to wait for the conduction to happen through the water because you don't have turbulence. So you're not going to have things reacting fast enough if you don't have long probes into those big pipes. So now you're going to, be dealing with something that's prone to failure because of the length of it and the bending moment on it. Communications across the system is disadvantage that you require that as well. So to start off the talk about how this actually worked is look at our temperature measurement. So acronyms, ETS is energy transfer station, EWT is entering water temperature, LWT is leaving water temperature, and ETP is the energy transfer pipe. That's the big one in the middle of the DES loop. And the labeling, T1 is energy transfer station 1 entering water temperature, T2 is entering energy transfer station 1 leaving water temperature, and T3 is GHX1 leaving water temperature. I place the sensors on this system like that strategically. I'll let you know about that. And then all T4 through T9, I'm not going to repeat that. It's just different energy transfer station number, but it's the same deal. So what's critical is we know coming into a ground loop area, we know what the temperature is coming in, we know what the temperature is going out, and we know what the temperature is coming out of the ground loop. Super important for the next steps. So main pump control in a single pipe district geothermal. So we ramp the speed up and down based on the maximum temperature between energy transfer stations, and we ramp the pumps to maximum speed if any energy transfer pipe temperature is above or below the threshold. So if any temperature is getting too low or too high, we're going to bump those pumps up because we don't want to have freeze-ups in the system or overheating. More freeze-ups are the bigger concern. So we've got temperature differences we're calculating to figure out which one's the largest. It's the max temperature difference on that first bullet point on the left. So we've got the absolute temperature difference of T1 minus T8. So that's leaving ground heat exchanger 3 and coming into ground heat exchanger 1. So that's really measuring the effect of the cooling dominant load on the bottom left. And then the other two are similar. So now we get into the fun part. This was really neat. I went and I looked at sort of like how much energy I could actually save by having the ground heat exchanger, 3 ground heat exchanger pumps, and they were Magna 3 pumps, so I could talk to them through BACnet and control them through BACnet and everything. So I looked at how much energy I could save, how much I could cut down the power use on these pumps by winding them down and using the whole area of all of the ground heat exchangers together. And it was significant, like way more significant than running just one of them. So we played with that a little bit on site, and it was just awesome how it worked out. So identified the problem with the planned sequence, which was to start the ground heat exchanger downstream of the largest Dipl.T on the energy transfer pipe. So what does this do? What happens to ground heat exchanger 2 when we always put a heating dominant load upstream of it, and it starts based on the temperature difference between, say, T3 and T4 there, starts GHX2's pump. What happens to GHX2 over time, downstream of a heating dominant load? Yeah, it gets colder and colder and colder. What happens to GHX3 and GHX1? They get hotter and hotter and hotter. So I was like, oh, I can't do it like that. That's stupid. I can't do it like that. So we originally were looking at doing it like that, and I was thinking about it at night, and I was like, oh, well, what are we going to do? So the BACnet IP pumps helped a ton. And on my LinkedIn, I got like set up notes on that because I had to commission like 8 of them, and it's kind of hard to figure out on from reading the manuals. So I got a video on that. So it's a shortcut if you're ever programming a Magna 3 pump. You can check out my LinkedIn there. The challenges we overcame was, so what I did is I made it so that after 5 minutes of running a ground heat exchanger pump, you start measuring and storing the temperature coming out of the loop. And then if any of the temperatures on the main pipe gets too cold, you start the ground loop that was warmest, the last used ground loop that was warmest. A lot of the time you don't need to use a ground loop pump because you have energy transfer within the single pipe, and it keeps it within that threshold temperature. And it's also acting as a ground heat exchanger because of the buried pipe. So when that heating dominant load comes on, we're going to see T4 dropping in temperature. Maybe if those cooling dominant loads aren't coming on at all, we're going to see that T4 get below the threshold. So now, let's say GHX1 was the warmest because it's behind the warmest cooling dominant load. So then I would start GHX1 first because it has the most energy. So now, by doing that, we're spreading out the load using the sequence of operations automatically, right? So it's super important. Like, we are not taxing one ground loop over the other. We're giving them equal usage. So that's a huge takeaway. That's why I came here, to tell you guys about this. Like, if you're doing this in New York and you're doing energy integration, you could save millions of dollars with this, because you're gonna downsize your ground loop. If you're gonna size ground loop number 2 for the heating dominant load, it's gonna be way bigger than if you can share the energy. But the controls have to work. This is like lots and lots of logic behind the scenes. That's a whole presentation unto its own. So challenges that I had were the ground heat exchanger pumps were coming on too late, and then they were just starting up at 100% because I was waiting a little bit too long. So I made the threshold a little bit higher for them to start on the central loop, on the DES loop. So then they start a little bit sooner and then ramp up. And then what I also did is I put in off delays with shorter on delays. So if we get to the point where we're running 3 ground loop pumps, chances are we're going to be at that point pretty soon again anyways. So what I did is I just said, okay, When these pumps ramp down to minimum speed, we're going to keep them on for a few minutes just to, because we know the load might come back on, and the load did come back on, and then so the pumps stay on, but they stay on minimum speed. So instead of like having the pumps come on and boom, ramp up to maximum speed, and then chuck all this energy into the loop because it's getting too cold, and then overshoot, and then they ramp right down. And so like I solved that by just like leaving them on a little bit longer. Like if they were on already, chances are they're going to be needed again, right? So you put an off delay on them. My on delay was screwing everything up, so I shortened it. So that was a little bit of hair pulling there, so you don't have to do it. The way that we do the ground loop pumps is we, let's say in heating mode, we start the warmest one first, and then the second warmest, and then the third warmest. So we're getting the best energy into the loop. And we start them on minimum speed. But then once all three pumps are on, then we start ramping them up together. So now we're spreading out the load through all three loops all at once and maximizing our surface area. And then once all three pumps get to their spec flow rate, we have turbulence and full load conditions in each of the ground loops, and they're all sharing the energy together. Now that's going to keep the ground loop, the whole system, from going too high or too low because we're using the whole heat exchange available to us. Now on the same job, I had a pretty interesting thing happen that people have told me to cross the pipes on tanks and stuff, but this also happens on low loss headers. So the problem in heating mode, I was coming in the morning, all my heat pumps are tripped out. The radiant supply to the building was cool, so you can see the top right there. We've got the return from the radiant was short circling back to the radiant, and the return from the heat pumps was going back to the heat pumps. So all the heat pumps, they just ramped up, and they tripped out and went from one to the other through the night. And all four of my heat pumps are tripped out in the morning, and I got a hot header, and I'm like, what the heck is going on? So I watched it for a while, and I was like, this is not heating up the radiant loop, but I've got a clear higher temperature on the right-hand side here from the heat pumps, and I got a Dipl.T, but I don't have a proper Dipl.T on the radiant system for my tank. So what was happening is it was setting up flow within the tank and not mixing. And I've seen this happen on low loss headers between a ground loop and the source side of heat pumps. So look out for it. You've got to cross those loops so that it mixes through the low loss header, because when you're on, we had 3-inch pipes coming into this because when the pool comes on in the summertime, we need that flow through the tank. But when we're just doing radiant heating, we have so little flow that it trickles through the middle of the tank, and you get laminar flow through the tank, and it sets up these different flow paths, and the water in the middle of the tank is actually insulating the two different flow paths. So yeah, duh, you gotta cross the pipes up, right? So what did I do in this? Because we have got a bunch of finished 3-inch pipe, and I'm trying to finish up this job, so I got the electrician. I lucky I had like quite a few extra points on my controller. So I got the electricians to put in a small circulator pump that runs continuously from one side to the other, and it's hidden behind the tank. I showed the owner right away because he's a developer, and I wanted him to catch this on his buildings too. Like, I admitted it fully, but I still hid it behind the tank. Right? You can get there, it's okay, you just can't see it. So yeah. When I saw this in a low loss header, the ground loop was running at like 50 or 60, 55 or 60 degrees Fahrenheit, and we were getting like near freezing temperatures into the heat pump because the water was just going through one side of the low loss header, not mixing, and the heat pump loop was just getting colder and colder, and it was mixing a little bit, but not enough, right? So that's taxing the efficiency of the system for the life of the system because someone decided that we're going to assume that a low loss header is going to mix. Now, what's the definition of a low loss header? Well, it's a bloody big pipe, right? Low loss. That means it's not going to mix when you put little pipes on it because they don't have enough flow to make this big pipe mix. So you get that laminar flow. It's huge. And this is really, really important because you don't want this happening on a massive tank that you put in at the beginning of a district energy system that's only being used by a couple of buildings. Because it'll take to the build out of the system and on the peak days of the build out of the system to actually mix the tank if you do that, So you'll compromise the efficiency of the system for the life of the system. I hope that sinks in. So I've got some questions for the audience. Please call out some energy sources for energy integration systems. Energy sources, anybody? The ground maybe? Okay, lakes, sewage, drinking water, industrial processes, data centers, good job. Okay, what about sinks? I'm not helping this time. Okay, good stuff, except ice rink is an energy source, not a sink. You're learning. Growth mindset. What is one of the most important factors to consider with two-tank, three-way valve changeover systems? Yes, leakage across the valves. Select the right valves. Make sure they work.
Is that spec in the valve submittals? Is that something you're going to see from the manufacturers? I think I have that going on right now. I don't think I've seen it.
You have to read the fine print, right? Like, yeah. I had this guy who I worked for, and when I was a young engineer, right? And I was an engineer in training, and he's the P.Eng signing off on my job, and I'm like, dude, the valve manufacturer just told me we got 10% leakage across these three-way valves. He's like, Daniel, you're sweating the small stuff. I'm like, yeah, 10% leakage between the hot and the cold tank for the life of the system is not small stuff, buddy, right?
I've got an owner with his hand on a pipe, like,
Yeah. And then you got the operator who's watching the hot tank get cold when you're cooling the cold tank. And then it switches over right away, and you're heating the hot tank, you watch a cold tank come up in temperature. You definitely have crossover, and that's definitely a problem. And the job where I found that the worst, the ground loop in March at the end of heating system in a heating dominated climate was about 10 degrees Fahrenheit above the undisturbed ground temperature in March. Okay, so that means not only were we heating the whole building with equivalent of like draw a big box around the building, right? To heat up the ground loop, you have to have energy coming out of the building, right? So you have all the energy losses from the building coming from electricity, and then the ground getting heated up from electricity. So effectively, the building was running at lower than electric baseboard heat efficiency. Great job, guys. And they did that all over the place. So when you see this, it's a big deal. Every place where you have a hot tank where you hold chilled water, or yeah, and a chill tank where you hold hot water, that's a problem. I messed up there, but yeah, that's actually what happens, right? So, what is the primary advantage of using a water changeover system? Water changeover is when we've got the three-way valves on both sides or six-way valves on both sides. Yeah, simultaneous heating and cooling. Right on, thank you. That's a really big takeaway, guys. So only a couple extra valves, and it leads to the problem I had, which is the next question. What needs to be equalized at some point in the sequence in a water changeover system? Pressures across hot, cold side, and the ground loop. Although the ground loop is a big expansion tank and can expand and contract like you wouldn't believe and take it all up. But, it doesn't hurt to open them all up. So my idea has been like, well, we have 3 expansion tanks, 1 for each system, and then like a really, really small line connecting the 3. So then whenever the system turns off and goes into a different mode, you just pop those open for a minute when you're waiting for the delay on the heat pump start or something, like just to make it, because what was happening is like you start up and you're in heating mode, your hot system, your tank goes and it compensates for the expansion, and then your makeup tank makes up water into the hot system. You got it all at pressure, then you switch over to cooling, and then you suck a whole bunch of water out of that, and then your makeup tank pushes the water into the cooling system. Now your cooling system's up at pressure, right? But then it just, by the expansion, it tosses it back and forth, and then you end up having water come out the relief. And I was thinking, well, man, this relief manufacturer sucks, right? That's what I first thought. I'm like, no. They can't suck, because then they'd be recalling this stuff, right? It wouldn't be safe. So then we figured it out, and yeah, it was quite a little bit of an eye-opener. Big deal. What is a potential way to enable maintenance on the energy transfer pipe in a single pipe DES while keeping a mission critical application going? Backup heat and cooling, that's right. You need it. If you've got a mission critical system and it's connected to a district energy system, eventually you're gonna need to turn off the district energy system, because someone's gonna dig into it with a backhoe or do something and drop all your glycol or have a big leak or something. And if it doesn't happen, well, you're blessed, right? Like, sorry, but I've been there, right? Like this one district energy system, the heating hot water system, had been leaking since the very beginning, and went and looked at the water meter on the makeup, and it was all full, the water was all orange, right? So they had like a 20 gallon per minute leak off the heating hot water system. The 100 boreholes were frozen after like 3 years. It's coming in at -3 Celsius. From the field in at -3 Celsius. We're losing, they've lost a bunch of compressors, a mega bunch of compressors. They lost the compressors, and like, yeah, it was, okay. So the contractor actually wanted to replace the expansion tanks, and they're massive 1,500 gallon expansion tanks, and there's 2 of them. And I approached him and said, well, why do you want to change out these expansion tanks? He says, well, where the bladder's joined, it's joined around there, it corrodes, and the expansion tank is losing pressure. I'm like, well, how did you test that? He says, oh, I filled it with air, and then I waited, and the pressure dropped. I'm like, you used a compressor to fill it with air, right? You do know the compression puts heat into that, and then when it cooled off from the makeup water going into the leak to service the heating hot water system, yeah, of course your pressure dropped. You didn't fill the tank. So then I looked at the tank specs, and it's actually a bladder that's hung on the inside, a full exception bladder, off of the top nozzle flange. There is no rim around it. The guy just wanted to sell another tank. So yeah, this stuff happens. It happens on a big scale. You need to have some sort of backup if you're gonna do mission critical. Like, you don't wanna be in that situation, right? What is the problem with always having the same ground heat exchanger downstream of a heating or cooling dominated load attached to a single pipe district energy system? So downstream of a heating dominant load, your ground loop gets cold. Downstream of a cooling dominant load, your ground gets too hot. So that's why we shared it. That's why when one pump's turned on minimum, and we still have delay run out, and we still have a call for cooling or heating into the main loop, then we'll turn on the next pump on minimum, then the next pump on minimum, and share it around. And then ramp them together after that. How do you pipe a buffer tank that has large ports but often has low flow? Cross them up, that's right. Okay, good job, guys. Now, please feel free to ask questions here and find me after the presentation, and I'll talk your ears off if you're interested in this stuff. Alternatively, please feel free to check out my articles, tips, and comments on LinkedIn. Some of my articles are also on the Altum Engineering webpage. The best way to reach me directly is to start a post on LinkedIn, so our networks can benefit from the Q&A. I want to share the information and experiences from the last 23 years of working in this field, so we can decarbonize the planet together in a timely and appropriate manner. You can also email me or submit your information on the Altum contact page or on our website. Thanks everyone for attending, participating, and following up on this. Right.
Thanks a lot. This is Pete Skinner. You really enlivened the end of the afternoon, much more than that cookie did. Let me ask you, you know, your single loop system didn't feature that buffer tank. And I couldn't understand how you would not have a buffer tank, and you also didn't have the expansion tank depicted there. Can you maybe bring that one back up and tell me where in the system it was? Because maybe where you put it might have all kinds of ramifications that I can't even dream of. Thanks.
Okay, well, this is a district system, right? So it would have an expansion tank at the inlet to the main pumps. But the intent of this is to have a really low loss system on the central, on the district system, on the middle system. So you're not going to have a huge drop in pressure, so it doesn't really matter where you put the expansion tank. You should really be putting it at the inlet to the main pumps, but you've also got, you know, like other pumps in the system that need to see that pressure. So you got to work out all your pressures and figure it out. But we just put a small one in this. This is a pilot. Scale one is only 4-inch mainline pipe, right? Oh, I forgot to mention. My idea was to make this whole central piping thing in downtown Manhattan could be the water lines. And then you pump the water lines and then do a return on them. But you need to do another connection for each load, right, on there, each building. So what you could do is you could actually connect the water lines between two buildings, and then you got your supply and return off the existing system, and then draw your water off of that. That's my idea for that. And then circulate it back to the reservoir, and you got a big ass open loop system. You don't have to open any roads up. Rad, right? Do it. Good luck. Do it! Yeah, that's why you don't want to tear up the streets, bud. Right? You got to figure out something that's going to work, and it's not going to be a sewage system, because who's going to maintain something that takes raw sewage and pulls heat out of it? Who's gonna do the parts for that, right? Like, I don't know, right? But you're gonna have all sorts of confined space entry issues. You're gonna have health safety issues. You're gonna have fats, oils, and greases coagulating. If you start doing a whole downtown Manhattan or big city off of, wastewater treatment, and you're cooling all that sewage, you're gonna have coagulation of oils and greases, and then you're gonna have proprietary systems in each building that need new parts, right? So do it off the domestic water lines. They're already there. It's a clean source of energy. You can recirc back to the reservoir. Now you gotta deal with municipal people, which is really difficult, but that's your challenge, not mine. I don't do the people part. I program stuff.
Anybody else?
Hey, thank you for the presentation, Daniel. Hey, a question with the district arrangement like this, and I really liked your description of the approach for mitigating the temperature impacts on the different ground heat exchangers. Would you ever contemplate turning the flow direction in your single pipe and turning that around? Would that be something that you would contemplate periodically changing that over?
Possibly, but you'd have to have your temperatures on both sides of the ground heat exchanger then, right? Because your leaving water temperature would come out of a different pipe then, and then you'd have to flip those pumps around too. So I would say no, once you get it going one direction. I forgot to mention, Ed Lorenz came up with this whole idea. Ed, stand up. This is Ed's plan. He got me onto the job. He got me doing the controls. I just came up with the idea on how to make it happen with the. So Ed's idea is on the central pumping, how to do that, and then I came up with the idea on the energy sharing with the ground loops. But Ed did the design and brought me onto the job, and I'm very grateful for that. Thanks, Ed.
was talking to a friend that I met here, and he sells supplies, and my question is, he said that they put like, that they have a tank that they can put in the ground, a plastic to make like an open loop, but it's like a closed vertical loop, and they fill the container, it's a 20 by 30 up with water, and then they put copper pipe down there. But I told him, what about taking the copper pipe, the soft copper pipe to the house? If you get a puncture in it, there goes your new test theory. So just something, and he was talking about solar to the ground loop too, to generate some heat. So just something to think about. But we are a not-for-profit, and we would like to put ground source heat pump into our building, and I'm certified ground source heat pump installer. So I wanted to know, we don't want like one 10-ton system. If one goes down, if there's a problem, then nobody has any heat. So what do you recommend? And I'd like to get your number. What do you recommend for us to have different loops for each? I'd like to put in 1-ton systems for each apartment.
Yeah, so on this system, the contractor went a little crazy with ordering pumps for every radiant zone and stuff, so we ended up with 46 different pumps, but we only have 3 models of pumps. So we can shelf one of the pump stations has 2 pumps in it, the other ones just have empty valves. So we can take that spare pump, that we have a duty and standby pump in one location, but we can take the standby pump and use it in multiple locations. And I do that on remote systems in the islands on the west coast of BC, where you have, it takes you all day or longer to get there. So, best thing is have multiple items that are the same and incorporate them into your system so that you can have that backup item be a backup for many locations. Right, so I've seen like these systems where people have like 3 different heat pump sizes in the plant, and I'm like, why did you do that? Right, why don't you just make 3 the same and like get one part for that fails will service all 3 heat pumps if one of them fails. So also, it's really important to duty cycle the heat pumps, I find. So like if you had like say 4 heat pumps. We did this distillery, and they turned off the auto rotation on me on the heat pumps. And the only problem after 6 years of doing this energy integration system is we're a really complex geothermal system for the distillery. Ed got me on that one too. Thanks, Ed. Was that first unit actually had a failure from corrosion under insulation on its evaporator because it was always starting first. So that always had the most condensation in a space. So yeah, lots of duplicates of stuff and duty cycle the stuff so it gets equal use and gets started regularly. And best way to keep something alive is use it once in a while. It's just like exercising, right?
Hey, when you're assessing temperature of each individual GHX to see which should be the active relative to current load dominance in the overall system, are you sampling that by running a pump to get your sort of actual ground temp, or are you just taking the last leaving water temperature as your reference temp?
Yeah, so what we're doing in there is we wait for 5 minutes or whatever delay we want to put in there. It's an adjustable delay by the operator. So after the ground loop pump starts, it's got a delay before it measures the water coming out of it, because I could see like, slugs coming from the header, right? And it's really cold all of a sudden and it goes warm again. Yeah. And then because it does run on a little bit, like, you might get short cycling through one of the loops if it's shorter, right? When you're running in Lavender, but
kind of ramp one, and you have variable speed pumps here. You can kind of play with. Okay, I'm going to drop and rise based on which one's active. Turn the one off.
Yeah, you're welcome. But yeah, it's measuring that temperature right up until when it stops. When it stops, then it restarts that start timer for sensing the temperature. We did that on a solar recharge system, also with Ed. So it's frozen ground loop, we're using solar thermal to recharge it, and we don't have like probes down in the ground. I see all these people like putting probes down in the ground and stuff so they can measure the ground temperature. So like run your pump for a bit, right? You'll see the temperature, it comes out the pipe, right? So, but we learned that the hard way because I was measuring the temperature all the time, and we eventually were measuring the mechanical room temperature, and the solar system wasn't turning on because I was like, okay, well, we clearly need to run this pump once in a while to get a sample, right, and see what the ground temperature is actually at, right? But that's a whole other presentation in Tampa, Ashbury, Tampa, on that system, because now we have like 3 years of data, and it's getting warmer and warmer. Like, there's a big block of ice, and then yeah, we're thawing it a little bit more each year. It works great. It's amazing. It shortens your ground loop too. So if you have a heating dominated loop using inexpensive like solar thermal, in the springtime when you have near freezing water going into these solar system, it just sucks up the energy like you wouldn't believe. Like normal solar systems are going to wait till that panel gets warm, right? But if you're putting refrigerated liquid into a black panel in the spring sun, it sucks up a ton of energy. So you can balance that loop out, and it's a cheap component. You can use these, we use these, a heat exchanger and these little polypropylene mats that you use for pool heating. They're not even glazed. Like you could toss it and replace it easy, and it'll be a couple $100 kind of thing, right? So that's a lot cheaper than borehole. Yeah, but in Florida, you might not have such a heating dominant load unless it's an aquatic center or a greenhouse, or yeah, you wouldn't freeze it up. Thank you for your time.